Hello students, in this video we will see the deviation of actual gas turbine cycles from the ideal gas turbine cycles, and we will also see what are the factors that are responsible for the deviation of the actual gas cycles or Brayton cycle, and we will see further we will also see the effect that produces by the actual gas turbine cycles. Okay, since we know that the factors which are responsible for the deviation of actual cycles from the ideal cycles are, since we know that the theoretical or ideal Brayton cycle is completely reversible in nature. Okay, but due to the internal friction and turbulence, there is a reheating takes place in the compressor and turbine. Therefore, the isentropic or reversible adiabatic process, therefore the isentropic or reversible adiabatic process or reversible adiabatic process will no longer isentropic. This happens because of the irreversibility caused in the system due to the internal friction and the turbulence. Internal friction and turbulence. Turbulence is something that there is a random mixing of the working fluid while it is compressed and expanded in the compression in turbines. Okay, so the effect of this is the temperature, or you can say the actual temperature after compression and expansion are higher than the ideal cycle. Okay, this is the major factor that is responsible for the drastic change in the actual gas turbine cycles, or you can say the actual Brayton cycle. Okay, the another thing is that there is also change in the work supplied and the work produced in the cycle. So you can say due to these irreversibilities that are caused due to the frictional force and turbulence, the actual work supplied to compressor is more, and actual work output to the turbine is less because of irreversibility generated in the system. we have discussed this irreversibility is generated due to the frictional force, internal friction in the turbulence. So I can draw the layout of the gas power plant. This is the compressor inlet at point 1. After compression, there is a combustion chamber. This is shaft, coupling shaft, on which both compressor and turbines are mounted. This is exit, this is output shaft. So this is compressor, this is combustion chamber, this is turbine. Okay, so here first enters at point 1, atmospheric air enters with mass flow rate ma, and after compression it enters to the combustion chamber, and in the combustion chamber there is a supply of fuel. Let the mf is the mass flow rate of the fuel. So after combustion the gas is generated, or you can say the flue gas is generated at point 3 as the mixture of ma dot plus mf dot. This is the mass of the gases generated after the combustion. So these gases are expanded in the turbine and will produce the shaft work W mechanical at the output. And after expansion, exhaust takes place into the atmosphere directly, because this is the open gas turbine cycles. Okay, so this is the layout of the plant, and we can draw the TS diagram also for the actual cycles. These are the diverging lines. This is the actual, this is the ideal compression 1 to 2. But due to the irreversibility, frictional force, there is a deviation of process 1 to 2 days. This is the actual compression takes place in the compressor. Okay, now 2 days, 2 to 2 days, and 2 days to 3 is a combustion process. 3 to 4 is a isentropic expansion, but this isentropic expansion deviated due to the irreversibility in the system. And 3 to 4 days is the actual expansion occurred in the turbine, and 4 days to 1 is the heat rejection. 4 days to 1 is a heat rejection. So we can see very clear cut in the diagram that is the actual temperature after compression is higher. T2 dash is higher than the ideal cycle temperature, that is T2. This is because of irreversibility caused due to the frictional force and the turbulence in the system. Okay, and this can also be seen at the turbine, that is T4. T4 is higher than T4 dash is higher than the T4. This is again because of the irreversibility in the system. this pressure P1 equal to P4 equal to P4 dash. Here P2 equal to P2 dash equal to P3. Constant pressure lines are diverging lines on the TS diagram. So okay, now we can write 1, 2, 3, 4, 1. This cycle is called ideal Brayton cycle, and the cycle thermodynamic cycle 1, 2 dash, 3, 4 dash, 1 is the actual Brayton cycle. Okay, so okay, here Ma dot is the mass flow rate of air, and Mf dash is a mass flow rate of fuel. Here the mass flow rate of fuel is also introduced, and we also introduce the Cp of fuel, because here the specific heats are not constant, because this is an actual process, and we have assumed that in case of theoretical Brayton cycle or ideal Brayton cycle, the Cp will not change with respect to the same temperature, but here in the actual case the Cp is changing with respect to temperature as fuel is entered. That's why the combustion products have the different Cp. Okay, so we call that Cp of gases. We can write the efficiency of these machines. Machines are turbine and compressors. That's why the name machine efficiency is introduced in this case. These efficiencies will overcome the effect of isentropic and actual expansion and compression processes in this actual cycle. Okay, so we can write the compressor efficiency. This is compressor. C denotes compressor. Efficiency of the compressor is the isentropic work done to the actual work done. This is the efficiency of the compressor, and it can be written in terms of temperatures. Isentropic process is 1 to 2, so T2 minus T1 is isentropic compression divided by the work supplied in the actual compression, that is T2 dash minus T1. This is the compressor efficiency. Okay, now the turbine efficiency we can write W of actual divided by W of isentropic. Okay, so the actual expansion is 3 to 4 dash. That's why we can write T3 minus T4 dash divided by isentropic expansion 3 to 4, T3 minus T4. These efficiencies are introduced to find the unknown temperatures, or you can say the actual temperatures of the cycle. Okay, we can also write the compressor work WC, or the actual compressor work. WC is the actual compressor work is equal to MA dot times Cp of air multiplied by T2 dash minus T1 is the actual work supplied to the compression. 1 to 2 dash is the actual compression. 1 to 2 dash is the actual compression. Cp of A is the specific heat of air. Ma dot is the mass flow rate of the air. Okay, similar pattern we can also write the turbine work. actual turbine work at the actual turbine work is equal to turbine is in between 3 to 4. 3 to 4, that's the actual expansion, and at point 3 the mass flow rate is ma dot plus mf dot and Cp of gases multiplied by T3 minus T4 dash. This is the actual expansion work done. Okay. Cp of G is the specific heat of gas or the product of combustion. It comprises of air plus fuel mixture. Okay. And we can also write the heat supplied at the combustion chamber Qs is written as mass flow rate is given mf dot multiplied by calorific value of the fuel. So this is the heat supplied in terms of calorific value of the fuel. We can also write the heat supplied in terms of temperatures, that is T3 minus T2 dash. You can also write this heat supplied in terms of temperatures. If you are interested to write heat supplied now in between 3 to 4 process. This is the heat supplied Qs, and the heat rejection is QR. This is the heat rejection. T4 dash and 1 is the heat rejection. Okay. So if you are interested to write the heat supplied in terms of temperature, so we can write T3 minus T4, and we know that at point 3 the mass flow rate is Ma plus Mf multiplied by Cp of gas multiplied by T3 minus 2 dash at 2 dash is the point before the combustion. So I can write Ma dot multiplied by Cp of air multiplied by T2 dash. This is the actual heat supplied to the combustion chamber.